Hi, in today's video we're going to talk about section 13.2 of Stewart, which is about derivatives and integrals of vector functions. As you can see, this video we're going to talk about derivatives. We're going to try to give you lots of chance to practice. A lot of students in a class like this find they're rusty with differentiation, especially after spending all of Unit 12 not doing any differentiation at all. So please take the time to watch, follow along. It should be really easy after you warm back up your differentiation skills, and there should be a nice section. Here we go. Jinx is in. So, derivatives work the way you would expect. You might remember in 2D, formally f prime of x was defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. And eventually we worked our way through that we weren't even using that rule anymore, but we understand the idea was that we're doing the limit of a bunch of secant lines to get the tangent line. So if I was doing the limit of a bunch of secant lines going through those 2 points, and I got closer and closer, eventually what I would do, as my point gets closer and closer and closer, is get the tangent line at the point I'm interested in. And the derivative was the slope of that tangent. So what about in 3D? We have very similar situation. We have r, we'll call it r prime of t. We're stuck, we don't want to use x because one of the components will probably be called x. And it's going to be the same exact setup. We're going to manipulate, perturb, is the formal word. We're going to perturb t a little bit and do the limit of a bunch of tangent lines. Sorry, the limit of a bunch of secant lines to get a tangent line. So we have a space curve floating out here. We might have a line connecting two special points. It's still a secant line. And we want to take the limit of these secant lines along the curve until we find the three-dimensional line that's tangent right at the space we want, whose slope, whose orientation in space matches the orientation, the space curve at that point. Basically, it's the same exact idea. We're going to find tangent lines. We're going to find velocities, instantaneous velocities, all that sort of stuff. The big theorem, and we're not going to prove it. There's a proof in the book. But that r prime of t is, okay, well, I'll say it as a theorem. If r of t is f of t, g of t, and then h of t, now h is not the change, it's the function, then r prime is exactly what you would think. F prime, g prime, h prime. Very, very basic stuff. We're not going to prove it. We're not going to do any limit definitions of derivatives. We just want to practice right now. So let's have some warm-ups. Example. I'm going to write these down and see what you remember. Feel free to pause and unpause the video at your leisure. So this was the twisted cubic from the last video. This one should be very straightforward. If you can't do this, I'd be sincerely worried about you and whether you should be in this class, as that means I'm pretty sure you can do it. Did you learn differentiation? Then you can do this. I believe in you. For this one, find r prime, and you can even find the second derivative in the same exact way. Pause the video, try it out. 3, 2, 1. What's the derivative of t? Just 1, not 0. I hope you still wrote an I component. 2t in the j component. The power rule in the k component as well. If you find it easier, we do not have a preference over how you write it. You should not get that worried about seeing it either way. You need to be comfortable translating back and forth, but if it's easier for you, always feel free to change between notations. And so then what's the second derivative? Well, this will go to 0, this will go to 2, and this will go to 6t. Which is, of course, just 2j plus 6t. Okay. What do these represent? What do these represent? This vector is the direction vector of any line, of the tangent line to r of t, the space curve, at any t value. That's what it is. It's representing the direction vector. The same way we would have talked about slope in 2D. Recall chapter 12, we're mostly talking about direction vectors now, or orientations of the line. Couple more things to help refresh your memory. I'm going to go to the next page. Here's another r of t. Talk about square root of t in the I direction, 1 over t in the j direction, just to review some of the trickier parts. Natural log, you may have forgotten these differentiation rules. It might be nice for you to have a printout, or just to make sure you print out a sheet and look up all of these basic ones that you used to know. Go ahead and take a second and try to find that out. I'm going to go ahead and write one more. E to the negative t sine, e to the negative t cosine, adding some spice, and tan inverse t in the k hat direction. Almost forgot j. And here I just want you to figure out what r prime should be. So go ahead, pause it out, pause the video now, and try out all 3 problems. Feel free to unpause to check your work when you're ready. I'm going to start writing. 3, 2, 1. In general, it's best to leave this as a power rule, especially if we're going to differentiate again, which we know we are. -1 t to the -2 in the j component. And a lot of times we would write that as just minus plus 1 over t in the k component. You would probably see this in answer keys like this. I minus 1 over t squared j plus 1 over t k. But for differentiating, it's really best to go and keep it in the power form. 3 over 2 plus 2t to the -3 j minus t to the -2 k. Do you feel like you're refreshing your derivative knowledge? Does this sound familiar? Okay, this black example at the bottom, we're dealing with the product rule. So if you just did this whole thing and you didn't use the product rule, you messed up. We're going to need lots of parentheses here. First, times the derivative of sine is cosine, plus the second, sine t, times the derivative of the first in the I. All right, if you didn't remember that, try it again now. Try it right now. Try the product rule on the second one. E to the negative t times negative sine plus cosine t times negative e to the negative t. In the j component, and I'll have to sneak it in, plus 1 over 1 plus t squared in the k component. Do you remember all these rules? I'll tell you, sometimes it's hard for me, but I have them pretty well down, and I've been doing calculus forever at this point. So if you need a refresher, you could go back and watch some of my YouTube videos for those. You could just do some practice. You could look at Khan Academy. There's lots of options. It's really important that you still remember how to do derivatives. Long story short. Let's get into the theory here, folks. Let's get into the theory. So, sketch R of t, vector valued function with only two components. This should be easy for you by now. It's just like a parametric equation. I'll give you a domain. Find the point at t equals 3, pi over 3, sorry, t equals pi over 3. And then find the tangent vector at t equals pi over 3. All right. You should be able to do all of these on your own. If you need me to walk you through some of this, here I go. So pause the video, try out. You should be able to at least sketch it. Why should you be able to sketch? Because we know x equals 4 cosine t, y equals 2 sine t. This should be getting old at this point. So it'd be x over 4 equals cosine t, y over 2 equals sine t. It's getting so old that I might not even write this that many more times. X over 4 squared, y over 2 squared equals 1. We only had two components, so we are just going to sketch this in the xy plane. Apologies if anyone sat there and tried to sketch this in 3D space. So we're going to have coordinates like 4 and 2. And we're dealing with an ellipse. It probably should be more symmetric, but you know me, it's tough to draw. All right, so we have an ellipse-ish figure. My point, and this is the point we're going to be tangent to. That's what it means when we're dealing with both pi over 3's. So r of pi over 3, this should also be very easy for you all. Cosine of pi over 3, see, I say it's easy, but then I'm the one who gets the corrections, is 2. Sine of pi over 3 is going to be root 3 in this case. I think that's right. So we're talking about a point like up here. There's my point of tangency. And then we're going to talk about the tangent vector. So the tangent vector, the steps, just like in Calc 1, just like in AP Calc, differentiate first. We get negative 4 sine t, 2 cosine t. You can't plug in, then differentiate. If you plugged in and got 0 over 0, very common mistake, very bad mistake. And then we plug in pi over 3 to this function, obtaining negative 2 root 3 in the I direction and positive 1 in the J direction. what we normally will do, you have lots of questions like this on the assignment. What we normally will do, we will graph this at the point of tangency. So what that looks like is going back to the left, -2, and up 1. -2 root 3 that way, and up 1. It doesn't have to be exact, but we should see what this is doing is giving us an orientation. If the position vector is coming from the origin and touching there, first things first, I want to point out these are tangent. These are at a right angle from each other. Second of all, what we're showing is that's the velocity vector, so to speak, of the position of the object at that time. We can picture an orbit, literally a planetary orbit in Kepler's physics. We were talking about the planets are orbiting like an ellipse around the sun. Then what's happening is at this point, the velocity of our planet's in blue. It's going up and to the left. And then in the next instant, the gravitation is going to switch us to going this way, and then this way. And these are all the tangent vectors here. They're telling us how the curve is traveling. And so it gives us that counterclockwise orientation. So I want to say when we graph this, we want to make sure we put, if you graph tangent vector, a lot of years I see students not understand this. You graph the tangent vector with initial point. It doesn't have to be exact, but the initial point is at the point of tangency. I'm probably going to talk about this a lot, so I might abbreviate it SPOT. Ha ha ha. Okay, and so that's what I did here. That's all I'm saying with that. Because it should give you an idea of how we're rotating around the origin or how I'm moving along this curve. It does tell me the orientation of the curve, the direction of travel, and such. All right. New example. R of t. We'll stick with the plane curve for a second. E to the t, e to the -2t. Graph the tangent vector at t equals 0. Okay, so how are we going to sketch something like this? That should be your first goal. When we're trying to sketch this, I want x equals, y equals, and I want you to think about how you would go about eliminating the parameter. Pause the video, think about it right now. So you'd have e to the t, e to the -2t. The smoothest way to do this, folks, you could have made a natural log, but then I know a lot of students struggle with the algebra with the natural log, is to notice that y is e to the t to the -2. So then if I combine these two, I have y equals x to the -2, or 1 over x squared. And that would really help you sketch it. I think you would agree. All right, so let's do a sketch of what this guy looks like. What does 1 over x squared look like? 1 over x squared has a vertical asymptote and a horizontal asymptote. And at t equals 0, where are we? We're right here. T equals 0. Sorry, you can try it out. R of 0 is what? Did you get 0 over 0? You shouldn't have, because that's clearly not going to be on the curve. It's 1 comma 1 right here. So that's our position. And now I can figure out the direction of travel without plugging in a second coordinate. Why? We're going to try to do a r prime. And then we're going to try to figure out what r prime of 0 is. Can you do those things? Can you do each of those parts? So try it out. R prime should have been e to the t, and then negative 2 e to the t. And so r prime of 0 should have been 1 comma negative 2. So what does that look like? Sorry, negative 2t. It doesn't really affect r prime of 0. That's why I'm getting ahead of myself. So what does that look like? We're going to start it off with the initial point right here. What does it look like? 1 comma negative 2. It looks like go over 1, down negative 2. And it should look tangent to the curve. It should look tangent to the curve. And it should give you an idea of how my particle is traveling. My particle is traveling this way. Because at that point, it's going massively down and to the right. So we're now going to turn our attention to a different kind of tangent vector, specifically the unit tangent vector. These look like always t. It's going to be, what is a unit vector? You're going to take the derivative vector function and you divide by the length of that vector function. And I'm going to try to give you a general advice right now. If possible, evaluate first. A lot of questions will not ask you for the general unit tangent function. They'll say find the unit tangent vector at a specific time. So if we're trying to find the unit vector at a specific time, these things will get a lot easier. What am I saying? All this is, because we're just trying to have, instead of showing the magnitude of velocity, maybe we just want to get the direction of the velocity. If we're picturing this as a position function, then the derivative is a velocity, and we just want to understand where are we going? Where is our particle going at that instant, ignoring how fast it's going in that direction. So if r of t is 2 sine 2t in the I direction, plus 3 cosine 2t in the j direction, plus 3 in the k direction, find the unit tangent vector. Okay, you need to know that that's symbol for the unit tangent vector at t equals pi over 6. So, first step first. You need to get r prime of t. Hopefully you all feel comfortable doing that. Then we're going to evaluate first at pi over 6. And then we're going to have to figure out what to do next. So, pause the video, try it out. You might know what to do next. R prime. Did you get 4 cosine 2t in the I direction? Did you get negative 6 sine 2t in the j direction? Plus 0 in the k direction? It doesn't matter that much if you wrote the 0, but there should not be a component there anymore. And so when we plug in pi over 6, careful that we're multiplying by 2 here, folks. Careful that we multiply by 2 first, so it's pi over 3. We're talking about 2i minus 3 root 2 No, 2 root 3. No, 3 root 3. J. I know my trick. And then 0 in the k direction. So, now if I want to find t, right? Look at the formula for t. We're missing what r prime's length is. So if all I need to do here is figure out the length of r prime, let's do it the way we would do any other vector length. This is a chapter 12 concept. Do we remember chapter 12? It should be the x component squared plus the y component squared, which is 27, plus the z component squared, which is still 0, or root 31. So, t at pi over 6, notice there's no prime on the t. T at pi over 6 is the unit tangent vector, would be 1 over root 31. I'm dividing by the length, and I'm multiplying the vector. And what we'd have here is a vector with length 1 and the direction of the tangent vector we wanted. It would give us the exact direction vector of the tangent line at that point without having too big of a length. That's the idea we're trying to mod out by. Why do we say evaluate first? Well, if I try to find the length of r prime of t, what would that look like? That would look like the square root of 16 cosine squared 2t plus 36 sine squared of 2t, which is not the nicest function in the world, right? We don't usually want to look at it like that. That's usually like a very bad feeling, right? It's not helpful often. So could we come up with a general formula for t? Sure. But that would look something like this. So we'd have that whole expression in the bottom. And we'd have the typical or the actual function on the top. And this would always give us something with a length of 1. But we would say probably it's not that enlightening what's going on there exactly. So we don't usually write things like that. We don't usually write the unit tangent vector as a function. It's not going to be a nice function. It's not going to be easy to write. We will expect you to be able to do it. All right, the last thing I want to talk about is tangent lines. Same stuff, different course. Basically, you're going to need a point, the point of tangency, and a direction vector. And the direction vector here, it's going to be easiest to use r prime. That's it. Okay, and we're usually going to write our tangent line equation as parametric. So we're talking about x equals some initial number at, y equals the y initial number bt, z equals the z initial number plus ct, right? And these direction components are coming from r prime, and these guys are going to come from the point. Okay, it's really not going to be that bad. It's going to be very nice and straightforward. hopefully. Unless you need to review calculus in a much more serious fashion. So if I have r of t equals t plus 2 in the I component, 1 over t plus 1 in the j component, and 2 over t squared plus 4 in the k direction, can you find the tangent line? No, because we never ask you to find the tangent line formula. We want you to find the tangent line at t equals 2. Find the equation of a tangent line more formally. So the point should give you flashbacks to your calculus class. How are we going to get the point? We're going to do r of 2. Find that for me real quick. How are we going to get the direction or the orientation? So r should have been 2 in the I component, 1/3 in the j component, and 1/4 in the k component. This gives us an initial point. Okay, it's a vector. But remember, there's an equivalence between position vectors and points in the obvious way. 1/3, 1/4. How do I get the direction? Well, we start with doing r prime. Don't just plug in 2 and then differentiate. R prime. Seriously, sit, try it out. Can you take the derivative of these? You could last year, almost certainly. We're not doing the derivative of r of 2. We're doing the derivative of the equation. Did you get 1 over 2 root t plus 2? We're going to evaluate it, so I'm going to write it into the nicer form. For something like this, I'd probably have changed it to t plus 1 to the negative 1 power. You could use the quotient rule, but that seems like a pain. So I'd have negative 1 over t plus 1 quantity squared. Same thing for this one. I'd rather not use the quotient rule if possible, but there's a lot of things you can get wrong here. I believe it's negative 4t over t squared plus 4 quantity squared. I'm sorry, I left off my vector components. You need to have that. It's a do as I say, not as I do situation, you know? All right, you got to make sure you have all of those components. Please, please, please. Okay. So what's r prime of 2? I'm getting 1/4. Pause the video if you don't want other spoilers. I think this is not the hard part, though. Minus 1/9 in the j component. Minus 1/8 in the k component. And so our line, our linear equation is going to be x equals 2 plus 1/4 t. It is super important that that constant's 2 and the scalar multiple of t is from the direction vector, from the tangent vector, from the derivative. You should be able to do y and z. Go for it. 3, 2, 1. 1/3 minus 1/9 t. Did you forget that sign? It has to be negative. 1/4 minus 1/8 t. And that's really all there is to it. It's not that bad, I would say. If you want more examples, I didn't do the one that was in the book, so you could look at the book's examples. You'll definitely get the hang of it as long as you review your derivative knowledge and try to shake off the dust. In the next video, we'll talk about integrals and continue our adage that it's really just what you would expect to do. Hope you learned something new or had a nice review of differentiation, and I'll see you in the next one.